Okay, so we have a question here. So we are going to discuss again about the mass balance because we missed our tutorial on that last part, especially on the reactors. So I hope you still have a bit of understanding, or you still remember the concepts that we have discussed before. So we have this problem here. A biodegradable organic matter, oxygen and microorganisms are placed in a closed bottle. The microorganisms will use the oxygen, oxidizing the organic matter. The bottle can be treated as batch reactor. So we have as a batch reactor here. So this one is batch reactor, right? And the decay of oxygen as first order reaction, all right? Write the general mass balance equation for the bottle. Using Excel, calculate and plot the concentration of oxygen each day for a period of 5 days, starting with a concentration of 8 milligrams per liter and a rate constant of 0.35 per day. So what you can see from this example is basically the process of looking at the BOD5, right? So this is the process for determining BOD5. So as you mentioned by Nick before, if you have a process on, if you want to know the BOD of a certain solution, then you need to do this process for 5 days. So what is the solution for this one? So we have a solution here. All right. So what we have as a given first. So what are the given here? So we have the given. We have 5 days, of course. The time is 5 days. Then we have the K, which is around 0.35 per day. All right, so this is the K now, 0.45 per day. All right, and then what is this given here? Batch reactor. So we have a batch reactor. And the given is, it is, how to say? No, it's not writing. So this is batch reactor, and given is first order reaction, first order. All right, so the question for this one is basically write the general mass balance, calculate and plot the concentration of oxygen each day. So calculate and plot the concentration of oxygen each day. So that is the question for us now. So what do we do from here? From this example, we can say that so for a batch reactor, we have first order. What is the formula for this? Batch reactor. If you remember, the formula for this one is C sub T is equal to C sub O e to the minus KT. So this is a first order batch reactor formula for getting the final concentration, initial concentration, and this we have this rate constant as well as the time here. All right. So our question now is our to calculate and plot. Okay, plot the concentration of each oxygen each day. So we have to calculate and plot. So we, for example, day, and then we have the oxygen remaining. So this is oxygen remaining here, and this is the day. So this is milligrams per liter, and so we have day 0, 1, 2, 3, 4, 5. Okay, so in day 0 is 8 is given here. Is day 0 is 8 milligrams is given here in the problem, milligram per liter, and then we need to know what are the remaining oxygen in these parts here. All right, so that is the question, and we need to graph that one. So how do we do that? Is using the formula. All right, so it's just pretty simple. So we have the initial CO is 8 milligrams per liter. All right, K is given, time is given as different day, and T is our what we are supposed to work on. All right, so we can go to the Excel on that. So we have, if we have the CO here, okay, C sub O, which is equal to 8. So that is 8 milligrams per liter, right? And then we have the K, which is the rate constant, and the rate constant is 0.35 per day. So that is the rate constant. So this is per day. All right. And then what we're supposed to get is to determine the the CO is already 8 there, so we have to determine CT. All right, so we have day here, and then we have CT. So CT in this case, C sub T is the oxygen remaining. Right, so this oxygen remaining is milligrams per liter. All right, so that is the oxygen remaining for this problem. Okay, so we have one day, okay, then we have 2 days, right, and then we can have this thing here for 5 days, so BOD 5. All right, so we have that one. So we are now going to use the formula that was given before. So this is the formula here. CT is equal to CO e to the minus KT. So we use that one. So it equals, so CT equals CO. So CO is 8, all right? 8 times, okay, times EXP, exponent, KT minus KT. K, which is K, times the time of the day, all right? But in this case, okay, we'll make this one as constant, this one, all right? And then we can enter that one. So we have that one here, 5.63 milligrams per liter for day 1, and then we can just copy everything for different days as well, right? So it's the same. So we have the same formula there, and then the 0 day is actually 8, all right? So in that case, from 8, it becomes 1.4 in day 5. So that's the remaining because of the consumption, and then we can graph this one as, can use a graph here, okay? So we have that one, so this is day here. The x-axis is day, and the y-axis is the, how to say, this one is the remaining oxygen. So I will just not put the axis level anymore. So this is the day here. So 1, 0 day, 1, 2, 3, 4, 5. And this one is the remaining oxygen level at specific time. All right. So this is now you can see the BOD 5 of the this problem. All right. So this is now the answer for problem number 1. All right. The second one. For the following conditions, all right, for the following conditions, determine the whether a CMFR or a PFR is more efficient in removing a reactive compound from the waste stream under steady state conditions with a first order reaction. So these are the given. We have reactor volume, flow rate, and reaction rate coefficient of 0.05 per day. Right, so we already discussed about the different kinds of the various kinds of reactors, right? So we have CMFR and we have PFR, right? So what is meaning for this? PFR is plug flow reactor, right? Reactor. So if you remember before, it's a plug flow reactor. The mass here is flowing, but this one is not mixing with this one, right? Only this part, the radially they are mixing, but not this part and this part are not mixing. That is for this part and this part are not mixing. That is for plug flow reactor. By force, this is PFR. For the CMFR, which is the continuously mixed flow reactor, as I mentioned before, if there's an in and there's an out, right? So we have this process here, there's an in and there's an out for a continuously mixed flow reactor. So we have different kinds of reactors, and the question is which is more efficient? Okay, more efficient in removing a reactive compound. So if you are an engineer now, you are given the situation and then you are supposed to give a recommendation. Do you think a PFR will be good, or do you think a CMFR will be good? All right, so let's have, this is the different equations for various reactors. You have batch, plug flow, and CMFR, right? So this is for steady state condition, and you are said that it's already steady state condition as well, all right? So that's the steady state condition. So we get for a solution here. All right. So what are the given? So let's first put all the given. So volume, is it given? So volume, reactor volume is 280 cubic meter. Then we have the flow rate, also here, 14 cubic meter per day, right? And K, reaction coefficient, a rate coefficient is 0.05 per day, right? So those are the given. What is the question? Whether CMFR or, so define CMFR or PFR is better. Huh? CMFR or PFR, that's the question. So which one of the reactor would you recommend for that one? Okay, so in order to do that, okay, so we need to see which is more efficient, okay? More efficient. So we need to get the efficiency. So how to get the efficiency? All right, so for efficiency, normally, solution here, so let's A. For efficiency, we know that efficiency is basically, we have the initial concentration minus the final concentration over the initial concentration times 100%. So normally this is the formula for efficiency, right? So you have the initial minus the final, or a specific concentration over the initial, and then you can determine the efficiency, all right? So if you have that formula for efficiency, then we need to identify this, you know, what are the values for each of these terms here, all right? So let's try to first for CMFR. All right, for CMFR, our formula for CMFR for a first order reaction is here. This is a first order reaction formula. All right, so we can use that one for CMFR. So C sub T is equal to C sub O, C naught, plus K theta. Okay, okay. So this CT and C naught are over 1 plus K theta is basically the formula for CMFR. All right. So we are going to get this CO and CT, but we don't know exactly what is theta. All right. K is known. We already know what is K. So theta is basically the hydraulic what? What is this theta? Hydraulic residence time. Okay. The hydraulic residence time. So how do we get theta? Theta is basically coming from volume and volume flow rate, right? So we have V over Q is theta, right? So I will just put the unit, for example. So we have V, cubic meter, and Q is cubic meter per second. Cancel, right? So second is the result, which is time, right? So in this case, we can now have the V, which is given. So volume is 280 cubic meter. This is given here. And Q is 14 cubic meter per day. So in this case, the answer for this is 20 days. All right. So now we have the 20 days for the theta. All right. So now we will put these 20 days here in this equation. So C sub T equals C sub O, C naught plus K theta. So we have C naught over 1 plus, how much is K? Is 0.05. 0.05 times 20. All right. So this is day, and 0.05 per day is day. So we don't need to put the unit there. So it becomes, so if we have that one, okay. So we have CO and CT. Okay. We don't know what are CO and CT. So I want to put CO below CT now. So it becomes, okay, CT over C naught. Okay, it becomes this one. Put here, it becomes 1 over 1 plus 0.05 times 20. Okay. All right. So once we have that, then we can get calculate this one. It becomes 0.05. All right. So it means that CT over CO is equal to 0.05. Okay. So that's the meaning of that one now. All right. So if you look at this one, we can say from here, from this formula, or from this equation now, so CT is equal to 0.05 C naught. That's the meaning, right? It's the same. CT, C sub T is equal to 0.05 C naught, okay? So once we have that, what we can do now is calculate the efficiency. So efficiency, which is in this symbol, is equal to C naught minus C sub T over C naught times 100, as I give before. Okay, so with that, you can see from here, we have C sub T here, which is the same in this part, yeah? So we just incorporate that value. So C naught minus 0.05 C naught over C naught. Okay, what happens now? We can cancel C naught, all right? Times 100. Okay, so that's the part now. So what happens is that the answer for this is 50%. Okay, this is for CMFR. So that's 50% for CMFR. I'll make another page. So, all right, so I'll continue with that one. That is for CMFR at 50%. Okay, so the same way, we can now use for PFR. Okay, so C is PFR. All right, we will use the same process that we did. But first, we will have to identify what is the equation for PFR. So in this case, the equation for PFR, for plug flow, a reactor is this one. C sub T is equal to C naught times E to the minus K theta. All right, so that is the expression. Then we can put that expression here. C sub T is C naught times E to the minus K theta. All right, so that's the expression for plug flow reactor. All right, so we can also get again C, this one, CT over C naught is equal to E to the minus K theta. All right, and theta we already got 20 days. K we have. All right, so we can get this expression now. So E to the minus 0.05 times 20, right? It's the same as before, but it's different equation for plug flow. So we can get this part as C sub T over C naught is equal to 0.37. All right. So that is the ratio of C sub T over C naught, and then we can get again the efficiency. Okay. So the efficiency is C naught minus C sub T over C naught times 100%. Let me see if some chat. How did you get 50% for the efficiency? Okay, I will go back there and see. I'll just finish this one. I'll go back there if I made it wrong. Okay, C naught. Okay. C sub T is basically, C sub T is 0.37 C naught, right? Basically, this one here. Okay, so we can also put that one there. C naught minus 0.37 C naught over C naught times 100% is equal to 63%. All right, so this is now the efficiency for that process. All right, so let's go back to maybe I have made wrong. First one is 50%. So this is, what is this one? Oh, sorry. Yeah, you're right with that one. I was wrong with this one. This part, sorry. This is not 0.05. It should be 0.5. Sorry about that. Apologies, 0.5. I wrongly put it at. All right, that's 0.5. And so if it is 0.5, that's why you were confused. Thank you. That's 0.5. Then that one now results to 50%. Okay, so apologies for that. That's 50%. It's just a value. I hope I clarified that Yes, you're right, Mohammed, but I clarified that the value is 0.5. Please check if the value is 0.5, not 0.05, all right? Okay, thank you, Mohammed. Thank you for letting me know. All right, so I hope that one clarifies the way for getting the efficiency. So in this case, you can see from here is CMFR is 50% efficient, PFR is 63% efficient. So the answer for this one is PFR is better than CMFR in this case. So it means that we will choose PFR. All right, so that's the answer for that. The PFR is more efficient in terms of degrading the substances in this particular problem. Okay, so this is the problem we have on this part here. This is the first reaction or removing a reactive compound. So PFR is better in this case. All right. All right, so another example. In a wet climate, such as Sydney, the organic carbon present Sydney, when it's rainy season, it's really wet. The organic carbon present in municipal solid waste decays according to first order kinetics with a rate constant of 0.05 per year. Under drier conditions associated with drought, okay, the first order rate constant reduces to 0.025 per year. So you can see the rate constant for wet season is 0.05, but it's a dry season is 0.025. So it means that it decreases at a dry season. Calculate the time taken to remove 99% of the original solid waste. Okay, that is, everything is organic carbon in both cases. So you need to remove 99%. What can you say about the impacts of drought on this decay process? So what is the difference between wet and dry season? Okay, so what do we do with this one? What do we do with this one? We are not given anything except for the first order kinetics, right? So in this case, since we are not given is only first order kinetics, we can assume, right, a batch reactor. Okay, let's assume a batch reactor for this one. Okay, so we can have a similar way of doing that one in a previous problem, the first problem. We can assume a batch reactor, and we need to remove 99% removal, okay? That is the goal. The goal is to 99% removal of that organic carbon from municipal solid waste, all right? So we have K. K at wet condition is 0.05 per year. Oops, what happened? Per year. And K in dry condition is half, 0.025 per year. All right. So we need to get the K for oh no, not the K, but for 99% removal of such thing. All right. So in this case, what we need to do is basically, if we are going to get the batch reactor kinetics, so our formula is C sub T over is equal to C naught A to minus KT, right? So this is for the batch reactor, right? That's our formula for the batch reactor. Now, our goal is to get this time here, the time. So that's our goal. So we need to have C sub T and C naught as well. We need to know this relationship between the two. But we don't know, we are not given the actual value, all right? So we are not given with the actual value of C sub T and C naught, right? So what are we supposed to do for that case? Okay, let's start with a wet condition, wet climate. So 99% removal. What does it mean? What is the relationship between C sub T and C naught? All right. So if we have 99% removal, what we can see based from the previous solutions that we have, if we have this ratio, At 99% removal, it should be 0.01, right? So 99%, 100 minus 99% is 1, right? So that's 0.01. That is the relationship between these two. If you base it from our previous slide, I want you to work on this one. How did I get that one? Right? So I'm sure you will get this part as well. So it means that C sub T is equal to 0.01 C naught. All right? So that's the meaning of that one. Okay, so now we can put that one here. All right. So the C sub T is this one. So I will put it again. C sub naught e to the minus KT. So C sub T is 0.01 C naught is equal to C naught e to the minus K. Wet condition is 0.05 times T, which is the one that we're looking for, the time. All right. So C naught is canceled. Okay, there are 2 there, and then it becomes 0.01 equal to e to the minus 0.05 T. Okay, so now what should we do? We need to convert this one into the natural number here. So we have to add both in natural logarithmic. So ln. So we have to times ln here. So ln 0.01 is equal to minus 0.05 T, right? So now we have removed E by adding the ln here. So now ln 0.01, you have 0.05 here. So we got T is equal to ln 0.01 over minus 0.05. In this case, the answer is 92.1 years. That's quite a long time, right? So that is for the wet condition, right? So what shall we do for the dry condition? The same way, the same similar process. All right, dry climate. So this dry climate basically is the same. The only difference is K. The only difference in this case is K. Yeah, that's the only difference. So we will process the same way. So in this case, 0.01 coming from this part here. Okay, we go directly. 0.01 C naught e to the minus. Instead of 0.05 is how much was that? 0.25. 0.25 T. All right, cancel. So we have 0.01 e to the minus 0.025 T. Then ln 0.01 is equal to negative 0.025 T. So T is equal to 184.2 years. All right. Okay. So what was the question? It takes this long time. For this specific problem, it takes more than 90 years for the 99% removal, okay, of the organic carbon present. 99 years for this specific problem for wet. And of course, for dry, it doubles, about 184 years, right? So you can see the effect of the wet and dry season, but of course, this is just too long, all right? The K value may be too low, the example here, all right? So, but this example shows you that the effect of having the dry and wet condition has on the decay of particular material, okay? So that's an example for this reactor problem. Okay, I think, yeah, we go for more, not complicated, but I think we go back a bit of the mass balance and see if you still remember how to do these things before. 2 towns located directly across each other, operate municipal wastewater treatment plants, okay? This example is actually, it actually was given as a final exam 2 years ago for this subject, but we don't have final exam this time, so that's fine. 2 towns located directly across from each other operate municipal wastewater treatment plants situated along a river. The river flow is 50 million gallons per day, okay? And there's a conversion here. So 1 gallon is 3.78 liters. Coliforms coliform counts are used as a measure to determine a water's ability to transmit diseases to humans. So coliform is related to the bacteria or microorganisms. The coliform count in the river upstream of the 2 treatment plants is 3 coliforms or 3 FU per 100 ml. Town 1 discharges 3 milligrams per gallon per day, 3 million gallons per day, sorry, 3 million gallons per day of wastewater with a coliform count of 50 coliforms per 100 mils. And Town 2 discharges 10 megagallons per day of wastewater with a coliform count of 20 coliforms per 100 mils. Assume the state requires the downstream coliform count not exceed 5 coliforms per 100 mils. You are hired as an environmental engineering consultant. So you are hired as a consultant. And New South Wales wants to get your recommendations on the following. There are 2 questions. Is the state water quality standard being met downstream? So what is the state quality standard? 5 CFU per 100 mils. That's the standard. Assume coliforms do not die by the time they are measured downstream. All right, so there's no reaction there. All right, so that's the assumption. They do not die. So you can have a steady state and a conservative pollutant. If the state standard downstream is not met, the state is requesting Town 1, okay, so Town 1 is here, that it must treat its sewage further so the downstream standard is met. Use a mass balance approach. Is the state's request feasible or not feasible? Is it possible or not? What would be your recommendation to the state? All right, so 2 questions. So I think it's a very good scenario here. So let's try to look for the solution now. I'll put it there. Okay, so okay, schematic first. What is the schematic? Let's draw the schematic so we can really see what this means. Okay, 2 towns located directly across each other operate municipal plants situated along a river. Okay, so we have a river, okay, Town 1 and Town 2 because they are directly across each other, right? So that's Town 1 and Town 2. The river is flow is 50 million gallons per day, okay? So river flow is 50 million gallons per day. So flow Q 50 mgd, okay? And coliform are used as measure to determine the coliform in the rivers upstream of the 2 treatment plants is 3. Oh, sorry about that. Where is it? Okay. So the coliform count in the river upstream. So this is upstream here. This is downstream here. Okay. So they have to. It means up is the higher part, and downstream is here. So upstream is 3 coliforms per 100 ml. So 3 CFU per 100 ml. Okay, so we can see because everything is 3, so we can just delete 100 in case, but you can just put it here, 3 CFU per 100 ml. Right? So that's the concentration, C, of bacteria. And then Town 1 discharges 3 million gallons of per day of wastewater. Town 1, this is Town 1 here. So there's an input here. So we have Q1 is 3 mgd. And then coliform count. Okay, so we have C1 is 50. Okay, CFU per 100 mils. And then Town 2, 10 mg. So there's Town 2 here. So Q2 is 10 mgd. And then C2 is 20 CFU per ml, 100 ml. All right. So CFU is coliform forming units. That's the unit. So CFU is equal to coliform forming units. All right. And then what's the question here? So we have, so C, we have Q here, Q downstream. This is Q upstream, C upstream, Q downstream, and C downstream. Okay, So now we have our schematic. So I guess we can now directly go to the solution, right? So we can go to the solution now because we have the schematic. So our question is, what is this? And what is this? And we have everything is given. Okay, so this is solution. Letter A, this part here. So what is the assumption? Is the state water quality standard. So quality standard is 5 milligram per liter. Oh no, not milligram per liter, but 5 CFU per 100 mils. That is the standard that should be met here, okay? That is the standard at the downstream. So if it's met, so if it's 5 or less than, then it means it is met. If it's not, then it does not meet the standard. So what we can do is mass balance. So mass balance, assumption is steady state, right? And no reaction, okay? All right, so in the steady state, dm over dt, or mass in minus mass out plus minus r, yeah? So this one is 0 here. This one is 0 because steady state. So we have mass in is equal to mass out. So basically our mass balance before. So mass in is equal to mass out. Okay, so what is the mass in here? If you look at the schematic, that's why it's important to have a schematic, so you will have, you know, you can picture out the problem. So mass in is mass in because this is your control volume. Yeah, this is control volume now. You make a control volume. So mass in 1, this is mass in also, and this is mass out, all right? So from there, what is mass in is Cu, Qu plus C1, Q1, so this one, plus C2, Q2, this one, is equal to CD, QD, all right? So we have everything given, everything is given, right? Everything here, not given and not given. But since this is a steady state condition, what happens to QD? So mass flow rate is basically if you have a volumetric mass balance, so QD is just basically is equal to QU plus Q1 plus Q2, all right? So it's basically the addition of this, and this flow. That's the meaning of that for mass balance, and then we can determine CD, all right? So I think from there, we can input all necessary values. So Cu is 3 CFU per 100 mils times Q, which is Q here, 50, this one. Sorry. It's 50. Oh. So now we have 50, right? So we have 50 here, and MGD plus we have also 50 CFU, 100 mils times 30. What is 30? 3 MGD here is 3 plus this one here, 20 CFU per 100 mil times 10 MGD. So notice we did not convert anymore to liters because everything is gallons, so it should be okay. It's equal to CD. And then we put QD below, right? Because we're looking for CD, right? So CD, so QD. So I have to put it differently. So we have to put it like this. So CD, C sub D is equal to QD. So QD is basically the addition of this one. So 50 plus 3 plus 10 MGD, right? So that is the equation now. So everything is same units. So now the answer for C sub D is 7.9 CFU per 100 mils, which is, in this case, is, if this is the answer for C sub D, what does it mean? The answer is, the meaning is that this one is still, 7.9 is still greater than 5.0. 5.0 is the standard, right? That was the standard given. Okay, so the standard says it's 5, this one. So it means that this discharge is not good. All right, so it means that it's not meeting quality. Okay, so that's the meaning of that. Let me check if I'm still online. Limits not being obeyed. Yes, you're right with that one. You're very right with that one. So the second question is, the second question states, as in environmental, if the state standard downstream is not met, the state is requesting town 1, all right, only town 1, that it must treat its sewage further to the down, so that the downstream standard is met. So they're requesting town 1, okay, please try to reduce your concentration, please. So use a mass balance. Is the state's request feasible? Is it possible or not? What would be your recommendation to the state? So how do we do that? We are only requesting town 1 to change. All right. Okay. I will make another page. Is that? All right. So letter B is changing town 1 only. All right. So town 1, letter B. Town 1 request to go down with the concentration 1. So what would be the concentration of town 1 so that it can meet the standard of 5 CFU per 100 mils? Is it possible or not? So let's try. So we have still the same formula, right? This is the same formula here. The same, we use the same formula. But the thing is, if you look at here, this is CUQU, this is upstream, this is town 1 here. That is town 1, right? So I will just probably put it back. C sub D is a CUQU plus C1Q1 plus C2Q2 over QU plus Q1 plus Q2, right? That's the same. But we are requesting that it has to meet the standard. So we are given the standard, right? This standard is 5. Okay, this should be 5. So we need to put it here, 5 CFU per 100 mils. That is the standard. Now, the question is how much of concentration should be changed? So in that case, what we can do is CUQU plus X. X is a known concentration, right? Plus C2 Q2 over QU plus Q1 plus Q2. All right, so in that case, we have one unknown, only this town 1. This is town 1 concentration. How much this should change. All right, so if that's the case, we can input now all values. So we have 5. We have 5 here is equal to, okay, I'll just put directly 3 times 50. Everything is the same number, right? And then X times 3, okay, plus 20 times 10, okay, and then over 50 plus 10 plus 3, plus 3, the same. All right, so now we have X here. So we have to solve for X. By rearranging the equation, we should be able to solve the X. So X is basically the concentration, new concentration of town 1, so that it will meet 5 CFU per 100 ml of standard. So what is X? The answer for that is negative 12 CFU per 100 mils. That's X. So that means, what does it mean? What is the meaning of this? So the meaning of this one is that in order for, let me see the chat, not being 11 negative, yeah, so coliform is not possible as coliform cannot be negative. You're right with that, Mohammed, you're right with that. So it means that in order for the standard to be met, the town one should have a negative concentration, which is not possible, right? So it means that in this case, the combined flow of town 1 plus town 2 is not meeting the standard, or is exceeding the limit. Okay, so this is exceeding the limit. So what would you say? So this is an impossible task. Okay, so in this case, you have to find another way, probably to reduce town 1 and town 2. All right, so maybe your recommendation, you have to check again and get the value. If you want to reduce your that part of to meet the standard, maybe not only town 1 should reduce, but also town 2. All right, otherwise, if only town 1 is asked to reduce, it's impossible to do that. Okay, so you can have another round of calculation. If you see, if you reduce both town 1 and town 2, you should be able to meet the standard required for that specific discharge. All right, so that's the meaning, and that's the solution for this specific problem.